recording is started now. So we're going to jump into 3.1 quadratic functions and models. I did skip over the practice problems because I want to go ahead and get into this. If there's time tomorrow, we can go back to look at the practice problems. The practice problems are in your packet online, right, in the Google Classroom. So just to show you an idea what I'm talking about, those practice problems, you know. Well, it kind of gets lost. I go behind the screen and it says, hey, where you at? So it's found me now. I have to, yeah. Is it following me now? Yeah. Okay. So 3.1, we're talking about quadratic functions. Folks, this is going to be a review. We're going to analyze quadratic functions. Remember talking about transformations, moving left, right, up, down, stretch, vertical compress, reflection. That's the kind of stuff we're doing in 3.1. Okay. So it should be review. Okay. No radicals. It's got to have exponents because it's quadratics. Quadratics are x squared, right? Yeah. So, but we only do easy stuff in here. So we're going to stick to that theme. Okay, some of the basic functions we've talked about in the past. The function ax plus b. We've usually seen that as y equals mx plus b, right? So if you see ax plus b or mx plus b, that's going to be a line. F of x or y equals c. Well, c is a constant. Y equals c is going to be like a horizontal line, a flat line. And obviously the last one, that would be the parent function for a squaring function, y equals x squared. All of these are, in fact, polynomials. This is what a polynomial looks like. All polynomials take this shape. Okay, this is a mess. What does all this mean? I don't care what the highest exponent is. We're going to call it n. So when you write an equation in the standard form, you're going to write it with descending powers. So what are these a sub n minus 1? What's all that mean? All that means is every term in a polynomial has a coefficient. If you don't see a coefficient, then it's 1, right? So all these a sub n and a sub n minus 1s, it's just letting you know that there are coefficients. They're not necessarily the same. Could they be? Yes. You could have 3x squared plus 3x, couldn't you? Where the coefficients are both 3, okay? But it indicates that the coefficients could be different. The degree of this function is n. N is going to be your highest exponent. A sub n is the coefficient with the highest degree. So a sub n is going to be, I just lost the word. What is the coefficient of the term with the highest degree? The leading coefficient, because it's first. That's called the leading coefficient. Okay. Yeah, thank you. Sorry, I went on a little trip without y'all. Okay, so every one of these functions here is a quadratic. Some of them are more obvious than others. Okay. The first one, f of x equals x squared plus 6x plus 2. That is written in what's called standard form or general form. I meant general form. So general form of a polynomial has decreasing powers. What's that second one? We've seen it before. We called it something else. This book calls it something different. We gave it a different name. I don't remember. After we complete the square, we can determine what of the quadratic. Yeah. We called it, it started with a V. Yeah, by looking at this, you know where the vertex is, or you should know. Yeah. So we called this vertex form because by looking at this, I know the vertex is located at -1, -3. -1, -3. H, K, right? But in this text, they don't call it the vertex form. They call this standard form. So when it's in standard form, you can clearly see the vertex. H really doesn't have a form name. It's just a quadratic. How do I know it's a quadratic? exponent of 2, right? It's not in descending power. I know it's a quadratic because an exponent of 2. How about K? Is that a quadratic? Okay. So it's got an exponent of 2. So is it a quadratic? Is this in general form? Yeah, this is general form. Correct. C, no, C is not 0.
Sorry, B.
Yeah, B is 0. How about that last one? Is that a quadratic? Why? When you multiply it out, it's already what? So this is called factored form. This is factored form of a quadratic. Now, I bring this up because if you are working a homework problem or a test problem, and it says the answer needs to be in standard form, and if you answer it like this, even if you've got all the right numbers and all the right letters, is this standard form or is this general form? So this is could be technically the correct answer. It's not in the proper form. So if you answer like this, it's going to be counted wrong. So when you get frustrated on your homework, make sure if it says general form, you put it in general form. If it says standard form, your answer is in standard form. Okay. The simplest squaring function is going to be the parent quadratic function. The parent quadratic function is simply y equals x squared. The graph of a quadratic, what's it look like? A U. Okay. And that U is called a parabola. We see parabolas in real life. Where have you seen a parabola in real life? Throwing a football. A skate park. A rainbow. McDonald's. Okay. Okay. Yeah. So we see parabolas all over the place. Okay. So we know that parabolas are symmetric. You can fold them in half across the axis of symmetry. Okay. It's an imaginary line, axis of symmetry. We can have parabolas open up. We can have parabolas open down. We can have parabolas that are fat like me, or they can be skinny. Okay. I'm not going to throw anybody under the bus. Leading coefficient is positive means it opens up. If the leading coefficient is negative, it opens down. Anything new today so far? Nothing new? Can I just what? Okay, I'll wait a second. Yeah, it's right here in the picture. Leading, it opens up. Leading coefficient, it opens down. If the leading coefficient is negative, the vertex is the maximum because it's opening down. The leading coefficient is negative, I'm opening down, which means the top of the vertex, the top of the parabola is the vertex, which is the maximum point. When the leading coefficient is positive, the graph opens up. When the leading coefficient is negative, the graph opens down. The simplest quadratic is f of x equals ax squared. Nothing new there. It's almost a repeat of the last slide, actually. Huh? So let's talk about a graph when it has a vertex at 0, 0. Again, we're saying the same thing again. If the vertex is at 0, 0, if A is greater than 0, or if A is positive, the vertex is the minimum value. When A is negative and the vertex is at 0, 0, then the 0, 0 is going to be the maximum. I don't know why they put 3 slides in here that say the exact same thing. It must be very important. Okay. I'm moving on. Remember when we were doing transformations, I would say, okay, let's go ahead and graph the parent function first. And I would graph the y equals x squared. And then we would talk about the transformations from there. You know, where's the vertex going to go? You know, I would say, move it left 3 and up 4. Open it down. Make it skinny. Remember all that? That's what this slide's talking about. So start with the parent function. And you might actually start sometimes with, instead of starting with y equals x squared, if it's a transformation involving, say, 2x squared, maybe go ahead and graph just the basic 2x squared and then form it from there. Last semester. Okay, so sketch the graph of each quadratic function and compare it with the graph of y equals x squared. So if you look at this picture, ignore the black line, it's not there yet, okay? If you look at this picture, the light parabola there, that is a graph of y equals x squared. What does the 1/3 in part A do? Okay, it's less than 1, right? So if this is 1, less than 1, it's getting closer and closer and closer to a straight line. What happens at 0? You don't have a parabola anymore. And what happens when it starts becoming negative? That's when it starts opening down, right? So because this is less than 1, it's going to be a wider. And what did we call that last semester? 1/3. What did it do? Which way? Vertical compression by a factor of. Okay. Remember the gummy bear? If I never brought one in, but imagine a gummy bear between my fingers. If I compress the gummy bear, the material for the gummy bear is going to still be there, but it can't be as tall. So what happens to the gummy bear? Okay. It gets wider. B, it's not on the screen. Tell me about it. What's it going to look like? Okay, it's going to be skinnier. That's called a vertical stretch. Okay. So we're multiplying the function by 2, which is greater than 1. That's a vertical stretch. On part A, we're multiplying the function, the parent function, by 1/3. That's a vertical compression. Questions so far? So it's less than 1. Less than 1. And when I'm saying greater than 1 and less than 1, I'm talking about the absolute value of A. Obviously, a negative one's going to open down, and -6 is less than 1, right? But that's not a compression. Okay. We're not going to graph imaginary. So here's the graph of that second one. It does exactly what y'all said. It is a vertical stretch by a factor of 2. Moving on. So in the last example we looked at, we talked about coefficient A and what it does, and it affects the width of a parabola. It also affects the way it opens. When the absolute value of A is small, the parabola is wider. If the absolute value of A is large, the graph is going to be skinnier. The example on the left is the graph of f of x equals -x squared plus 1. What transformations take place in -x squared plus 1? The negative makes it reflect, opens down. The plus 1 makes it shifts the whole thing up 1. Okay, so here it is. The light graph is the parent function, y equals x squared. It has been now reflected and opening down. Obviously, that's the same thing. Shifted up 1 unit. And g of x equals x plus 2 squared minus 3. What does the 2 do? 2 to the left, down 3. So the parent function is graphed. The new graph is the exact same size. It's just been moved left 2, down 3. Is this a relief on what we've been doing? Okay. Okay, standard form. Standard form, what I've called in the past vertex form. I just say that to make the connection. Know that the textbook and the tests and the homework you're doing will not call it vertex form. They're going to call it standard form over and over and over again. Okay. But then they tell you right here, this form is especially convenient for sketching a parabola because it identifies the vertex of the parabola. And that's why we call it, most books call it the vertex form. Because when it's written in this form, I know exactly where that vertex is. The vertex is at the point HK. And then it goes on and says, okay, well, here's the equation, but A can't be 0. How come A can't be 0? Yeah, well, yeah, because if A was 0, I have no X. I would just have f of x equals k, which is going to be a horizontal line. Okay. To graph a parabola, it's helpful to begin by writing the quadratic function in standard form using the process of, okay, so this is going to be a little bit difficult part, but you should remember how to do it. This is called completing the square. I'm going to tell you before I move forward to their example, the way they do completing the square is a little different from the way I do it. Okay. I'm not going to, I don't plan on going back and showing you the way I do it again. You've seen the notes and stuff. We've done it in the past. You're fully welcome to do it the way I've showed you in the past, or you can adopt this way. Which way is better? They're both the same, essentially. So if you understand this one better, great. It doesn't matter to me. So to complete the square, if this is a perfect square, is it a perfect square? What do I have to do to complete that square? I have to add something. And because we're dealing with a function, if I'm balanced, if I add something to the side, I'm not balanced anymore. How do I balance myself? Can't add to the other side. I have to subtract it, right? I'm not going to drop it because my pen's already messed up. So if I take it back away, so if I add and subtract, what did I essentially do? You know, if I was to add 6 and immediately subtract 6, what did I really do? I added 0, right? I added nothing. Okay. So that's just what we're going to have to do. When we add something, we subtract it. Do y'all remember doing this? Okay. I attempted to teach you at one time. Okay. To find the x-intercepts, you have to solve the equation ax squared plus bx plus c equals 0. That equation can be solved by factoring, by completing the square, by the quadratic formula. So lots of ways to do this. However, ax squared plus bx plus c does not always factor, does it? And when it doesn't factor, then we've got other problems. Completing the square always works. And didn't we just do this last week? So here's completing the square. It works. Now let's talk about the easy way to do it. What's the easy way? Quadratic formula. Okay. So exact same concept. What happens when a parabola has no x-intercepts? Can we still graph it? Yeah, we can still graph it. We can still transform it. We can still find the vertex. We can still plot points and graph the parabola. Okay. So here's our problem. And I'm going to just talk through what they're doing here. They're going to complete the square on this quadratic. So the original function, y equals, or f of x equals 2x squared plus 8x plus 7. The square, we are completing the square on the x parts. We leave the constant alone. So the only thing I'm interested in on completing the square is the 2x squared plus 8x. Next step. In order to complete the square, a must be 1. If a is not 1, you have to factor out whatever the current a is. So in this case, my a is 2. And I don't care if this 8 was a 7, I would still factor out a 2. Okay, it's not as pretty, but I would still do it because I can factor a 2 out of a 7. Okay, it'd be 3.5, right? Okay, so they gave us an easy problem. As they said, okay, it has to be a 1, so to make this a 1, which gives me 2 times x squared plus 4x. So these two pieces right here are exactly the same. And there's the plus 7 I'm not going to mess with. Okay. Now, what do I need to complete the square on x squared plus 4x? What's needed? What's half of 4? What's 2 squared? So to complete this square, I have to add a 4. Now watch what they do. What they did was they added the 4 and subtracted the 4 inside that set of parentheses. Is that how I did it? I did it out here. Okay. I'm just going to go along and talk through what they did. Okay. So it's clear that by adding 4 and subtracting 4, I've effectively done nothing, correct? Okay. The next step that they do, they say, okay, well, because we've done that, I need to regroup my terms. So what they did was they took this part and wrote it down here. But that 2 is also distributed to this -4, right? And so that 2 with that -4 is right here.
They just moved the negative.
Yes. And then plus 7. So they've regrouped everything. Now, looking at this, can you simplify anything that you see right there right now? Well, that's not distributing, that's just multiplying. Okay, so -2 times 4 is -8. Can you combine that with the 7 that's already there? -8 plus 7 gives you, okay. Because we made x squared plus 4x plus 4 a perfect square, it factors into x plus 2 squared. So I now have 2 times x plus 2 squared, and you already told me that was -1. Okay. So looking at this, I can clearly see where the vertex is. The vertex of this parabola is at -2, -1. That 2 causes a vertical stretch. I can graph it. I do want to point out on the graph that they show here, they show, instead of showing y equals x squared at the beginning, they actually show y equals 2x squared. So what they did here on their graph is they went ahead and graphed it showing the stretch. Okay. And then what did they do after that? They moved it left 2, down 1. Just pick up this whole thing, left 2, down 1, and there's my new parabola. Questions on their process? Okay. In that figure, they also drew the that vertical line at -2 because that was the x value of the vertex. So in the previous figure, you actually saw the axis of symmetry drawn in. Finding minimums and maximums. Many of applications involve finding the maximum or minimum of a quadratic. We can complete the square. And once you complete this, what's the benefit of completing the square again of a parabola? It gets you the vertex form. What's the benefit of having the vertex form? I know where the vertex is. Well, if a parabola opens up, where's the vertex? If a parabola opens up, the vertex is at the bottom, which is the minimum. If a vertex opens down, if a parabola opens down, the vertex is at the maximum, right? And a lot of times we're actually about to work a problem, we're going to want to know what is the maximum height of an object. Okay. Yeah, I don't think I've ever messed with that formula. I honestly don't think I'd want to. Yeah. I mean, I guess we could try to use this formula and take the previous problem and see if we plugged A, B, and C in, if that would give us the answer instead of having to go through all the factoring and stuff. I've never done it. Okay. For time's sakes, I don't want to, because we still got to cover 2, 3. Okay. I know we have tomorrow for 2, 3, but then you have no time to work on problems in class. So where's the vertex? The vertex is at the point. If I just gave you standard form, to find the vertex, you don't have to put it in vertex form. To find the vertex, you need to figure out where the axis of symmetry is. And the equation for the axis of symmetry is x equals negative b over 2a. I write it a little different than they do. I don't like the negative out front. I like the negative on top with the b, because that's kind of built into the quadratic formula, right? X is equal to negative b plus or minus square. Okay, so know that this is comes from the quadratic formula. So if I had a quadratic in general form, I know what A is, I know what B is, I know what C is. Using that information, I can find the x value of the vertex. I can find the equation of the axis of symmetry. Once I know this value, if I plug this value into the function, that's going to give me the y that goes with it. I now have the vertex. Okay, so that's what this is showing here. And numbers 1 and 2 talk about stuff that we've already talked about. If A is positive, it opens up, so we have a minimum. If A is negative, it opens down, we have a maximum. Okay, word problem. The path of a baseball after being hit is given by the function f of x equals negative 0.0032x squared plus x plus 3. Okay, what's that graph look like? Parabola opening down. What else can you tell me about it? Really fat, really wide. Okay. What does x represent? Okay, so I swing, I hit the ball's moving that way. I'm just going to talk about a straight line right now. The ball's moving that direction, right? X tells me how far the ball is on the horizontal from home plate. Okay, what is f of x? That's how high it is at a given time. Okay, so the question asks, what's the maximum height? Okay. What kind of a path will the baseball fly in? It will be a parabolic flight. Okay, now we're ignoring wind resistance, we're ignoring we're ignoring all kinds of stuff. I'm pretty sure it will not fly in an exact parabola. If the wind's blowing in, it's going to go up, and actually could sometimes be coming back if the wind's blowing hard enough, right? Huh?
Last night I had a dream about me trying to figure out how high a baseball could get hit in the air.
Okay, this is just a hit. Okay, so where is the maximum height going to occur?
Wherever the X is there.
And the maximum is located at the, so let's find the vertex. So let's start off with the axis of symmetry, because the vertex is going to be on the axis of symmetry, right? And that is x equals negative b over 2a. Negative b, that would give us negative 1 over 2 times a. And a is not x. Okay, just the number. The number is a. Okay. And once you plug that into your calculator, looks like we have a negative divided by a negative, which is a positive, which is a good thing. The maximum height of this ball is actually going to be above the ground. If you get a negative, you done messed up, right? You done messed up, AA Ron, huh? Okay. So what do we get for x?
I don't know this.
Is it 156.25? Okay. Okay. So after the ball's hit, it's going up. After it's 156.25 feet away from home plate, it's at the maximum height. How high is it? How do we find out? What is f of 156.25? Which means take that function and plug it in. I don't remember this answer. I remember the other one from this morning, but I don't remember this answer. Once you say it. +3, yes. So what's it? That sounds right. What does that mean? Put it in context to the problem. Okay, the maximum ball, 81.125 feet. Okay. I'm gonna go on to the next slide because it has the same information for us. But we've worked it out there and see if they agree. Talking through it here, they've got the equation. That implies that A is negative 0.0032 and B is 1. How come they didn't mention C? It's not part of the formula, right? Okay. So here's the formula for the axis of symmetry. We plug our numbers in and we get 156.25 feet from home plate. Plug that value in to determine the maximum height of the baseball. It's 81.125 feet. Questions on that? All right, let's do some practice problems here. It says write the quadratic function in standard form. They gave us a function in general form. We need to convert that to standard form. How do I do that? Complete the square. I'm going to complete the square on that piece right there. So f of x equals. Let's complete that square. And I'll go ahead and work it their way. I'm okay with that. X squared minus 6x. What do I have to add to complete the square? What is b? What is b? Negative 6. What's half of negative 6? Negative 3. What's negative 3 squared? 9. Adding 9 completes the square. Since I'm staying inside the parentheses, because I added 9, I must subtract 9. Here's my plus 2. Now then, this is my perfect square. So f of x equals, what does that factor into? X something. Okay, here we go. What's half of b? Okay, there it is. Okay, so it's factored. Yeah, it's that simple. Okay, we chose that value for a reason. Okay, what's left? Okay, and guys, I went ahead and worked right through the parentheses like it wasn't there because there's no number out in front here. That makes sense? If there was a number out front here, I would have had to multiply that -9 by this number, which we'll see on this next problem. And so that's standard one. Number one is done. Okay. Yeah, I'd have to fly through this one. I'm just going to fly through this one real quick. I'm going to complete the square on that piece. No, I'm not going to be able to fly through this one because I've got to factor out a 7. To factor a 7 out of that, it's going to look like this. F of x equals, factoring out a 7 leaves me with x squared minus 1/7 x. Because what is 7 times a negative 1/7? 7 times 1/7 is 1. 7 times 1/7 is 1. So that would give me the negative 1 back. So then we have to figure out what's half of negative 1/7, which would be negative 1/14. Negative 1/14 squared would be positive 1/196. So I'd have to add a 1/96 and subtract a 1/196. So I'm not going to be able to work this one fast. I'll finish this one tomorrow, and then we're going to jump right into 2-3. Okay? Yes.